All right, guys, we're going to talk about the rules of exponents here. But before we get into the rules of exponents, it might be just a good idea just to review really quickly what exactly is an exponent, okay? And an exponent is essentially a way of communicating how many times to multiply a number. So if we were going to think about it, and we can choose easy numbers here, but if we were going to think about it, in a simple sense here of like, you know, 2 to the third power. We've got a couple different pieces here. And the first piece that we want to talk about here is going to be our base. Okay. And the base of an exponent is going to be this number here. And in this case, we got 2 to the third power, 2 cubed. And it's going to be this piece right there. And this is, again, what we call the base. Okay. And the next piece we want to talk about is this 3. Right? And the 3 here is going to be what's called our exponent. Okay? The exponent. Oops, I can't write. Exponent. Okay? And we need both these pieces to be able to do exponents. Otherwise, the whole thing kind of falls to pieces. And what this is communicating here is that we're taking 2 and we're taking this 2 here and we're multiplying it by itself 3 different times. So in this case, this 2 to the third really can be written out as 2 times 2 times 2. And you can see that this was just basically a way of writing this in a simpler form, right? So that we don't have to write this whole piece. We can just write that right there. And as we get into more complex stuff, this becomes increasingly useful to simplify the way we write expressions, mathematical expressions. But in this case, we got 2 times 2 times 2, or 2 cubed, right? So that's essentially what an exponent is. And when dealing with exponents, there are 7 main rules that we're going to discuss, and these rules of exponents should pretty much be enough, when accurately understood, to get you through the remainder of this course, as well as on into calculus, right? So these should be pretty useful and things that you will probably have to revisit over the next few years of your mathematical experience, right? So rule number 1, let's start with that. Rule number 1. So rule number 1 states that not x, but any number to the 0 power equals 1. And I'm going to write this with just an x here, but understand that x just represents any number. And we could replace that x with any number that we wanted to. And let's go ahead and do that. And what that's saying is if I had like 3, for example, to the 0 power, that's going to give me 1. And I think that this should make sense because remember that exponents are telling us how many times to multiply by our base here, right? And in this case, we're multiplying how many times? Well, 0 times. We're not multiplying at all. So what are we left with? We are left with just a 1. Okay? We're taking 1 and multiplying it by 1 and multiplying it by 3, 0 times. Okay? And so our resulting solution is going to be 1. So any number to the 0 power will always be 1. Rule number 2. Okay, rule number 2 states that any number to the negative power is going to be just that number, or 1 divided by that number to the same power, only positive. Or in other words, we take this base, we drop it into the denominator spot, and make our exponent positive. And that might seem a little abstract, so let's kind of talk about a more specific example. We could say 2 to the negative 2 power. Let's not do 2, let's do negative 1 just for the sake of not having the same number there. So 2 to the negative 1 power is going to be equal to 1 over 2 to the 1 power. I want 2 to the 1 power is what? Any number to the 1 power is just that number, right? So this is really just, 1/2. And we could plug that into our calculators and see, by the way, if we wanted to, 2, we would do the 2 with the little hat thing, and then parenthesis, negative 1, close parenthesis, like that. And we would get exactly this 1/2 or 0.5, depending on how your calculator wanted to, how you set your calculator up to communicate these answers. But that would be the same thing, right? And just to maybe do one more example with this, right? One more example real quick. If we had 2 to the, or let's do 3 this time, 3 to the negative 2, well, this is going to be the same thing, right, that we just talked about. So I'm going to take it, put it under 1. So I'd have 3, and instead of a negative 2, I'd have a positive 2. So I'd have 1 over 3 squared, and 3 squared is 9, so this would give me 1/9. Okay, and that's how we're going to handle negative exponents. And that should make sense to us, by the way, because, when we have positive numbers, our exponents are telling us how many times to multiply. And if we have negative numbers, which are the opposite of positive numbers, shouldn't we then do the opposite operation of multiplication? Well, what's the opposite of multiplication? Division, right? So it should make sense that instead of telling us how many times to multiply 1 by our base, it's now telling us how many times to divide 1 by our base. And in this second example here, we see to divide it by 1, or divide by 3 twice. And in this case, we see to divide by 1 or divide by 2 once, right? And so hopefully that makes some sense for you guys. Rule number 3. So rule number 3 deals with multiplying exponents. So if we have any numbers, or any exponents with the same base, which we'll just communicate with x again. So say I've got x to the a power, and a just represents some number, right? And x to the b power. So I've got the same base but different exponents. Whenever I have that, all I have to do is just add those exponents together. So I get x to the a plus b. Okay, x to the a plus b power. And hopefully this is making sense to you guys as well. But we could even think about it in a less abstract way here, guys, by let's just give these some values really quickly. And we can even just leave x exactly where it needs to be. That doesn't need to change. But for the sake of just switching everything up, let's say we've got 4 to the 2 power times 4 to the 3rd power. And, visually, I think that this will make sense if we expand this out. And so really what I've got here when I say 4 squared, or 4 to the 2 power, I've got 4 times 4, right? And that whole piece is being multiplied by 4 cubed, which is going to be 4 times 4 times 4. And when we do it this way, we can actually count out those exponents really easily. And I've got 1, or not those exponents, excuse me, count out the 4s really easily. I got 1, 2, 3, 4, 5. And so we know that this whole thing is going to be 4 to the 5th power. But again, this should make sense to us, because if we take, thinking about what we've talked about right here, right? 4, this would be 4 to the 2 plus 3, just like we did over here. Well, what's 2 plus 3? 2 plus 3 is 5. And that's exactly what we said it was going to be when we counted them all out like this. And so whenever we have exponents that are being multiplied by each other with the same base, we just add those exponents together. Okay? And rule number 4 is actually pretty similar to rule number 3. The only difference here is that instead of multiplying exponents with the same base, we're now dividing exponents with the same base. So I can write this out as x to the a divided by x to the b. And I think that some of you may already be getting there in your heads. When we're multiplying these, we add those exponents. So if we're multiplying, we add. If we're doing division, which is the opposite of multiplication, we should then have to do the opposite operation of addition, like we see here in the exponent here. So instead of adding our exponents, we should be subtracting them. So I would get a minus b. Now I will just say this really quickly. Remember that that addition and multiplication are associative, meaning that the order doesn't matter. For example, 2 times 4 is 8. 4 times 2 is 8. 2 plus 4 is 6, just like 4 plus 2 is 8. However, when we're dividing and subtracting, those two operations are not associative. So if 2 minus 4 is not the same thing as 4 minus 2. 2 minus 4 is negative 2, where 4 minus 2 is positive 2. Those are not the same thing. And so the order does matter here. So our numerator, the exponent numerator, and the numerator becomes the first part of our subtraction. So it's a subtract the denominator, which is our b. Okay, and that does matter. Otherwise, you're going to get things that are a little bit off as a result. Let's do an example of this though really quickly. So I could say let's do 3 to the 4 power divided by 3 to the, I don't know, 2 power. Okay, and in this case, we could expand this out if we wanted to really quickly. In the numerator, right, I would have 3 times 3 times 3 times 3, or 3 to the 4th, right, all divided by 3 squared, or 3 times 3. And you know, using our rules of fractions and things like that we've practiced since you know, like the 5th and 6th grade, we can just cancel out these factors that are the same. And so cancel this 3 would cancel out that 3, and this 3 would cancel out that 3, and I would be left with how many 3's? Well, 2. And we could go to this idea of our a minus b, of subtracting these exponents, and I would have 3 to the 4 minus 2. Well, what's 4 minus 2? It's 2, right? Which is exactly how many we can see that we have left right there. We have 2 3's left, or in other words, 3 squared, right? This principle, some of you guys, I think, already kind of intuitively understand that. Okay. Rule number 5, guys. Rule number 5 is our exponent of exponents rule. So whenever I'm taking the exponent of something with an exponent, so in this example, we could say like x to the a power all raised to the b power. And, you know, when we think about what to do with these exponents here, when we were multiplying them, we added them. When we were dividing them, we were subtracting them. Well, I can't add these together because that operation is already being used, and this is not the same thing as what we see in number 3. So I do have to come up with a different operation. What's left? You know, I've got multiplication and division, and since this is going to be increasing, I know it has to be multiplication. So this is going to be the same thing as x to the a times b power. And let's just give you a quick example of this to help you understand this. If I had 2 squared to the 3rd power, we can expand this out and just see what this is going to be. We know that by multiplying those, I should get 2 to the 6, right? This should equal 2 to the 6, but let's expand this out. I'm going to get 2 times 2, right? That's what I've got inside these parentheses. And then how many sets of these do I have? Well, I've got 3 of those. So there's 1. So 2 times 2, there's 2. And 2 times 2, there's 3. And I can count really quickly here as well. I've got 1, 2, 3, 4, 5, and 6 of these 2's, which is exactly what we predicted by multiplying those exponents together. And so I know that that 2 squared cubed is going to really be 2 to the 6th power. Okay, hopefully that makes sense to you guys. Rule number 6 is dealing kind of with the same thing, but it's the distributive property of exponents. So if I have something like this where I've got 2 different numbers, and I'll represent these with x and y, just know that these could be any 2 numbers that are not the same. And I'm taking this to the a power, just some other number, right? That's going to be equal to x to the a times y to the a. All I do is I just distribute that exponent through to both parts. Now this only works because I'm multiplying. Remember that that exponents are a way of expressing multiplication. So that works with multiplication just like this. If I had changed that operation and had an addition or a subtraction in there, that would be going over to our FOIL method that you guys remember from factoring quadratic functions, right? Because those operations are not the same, but because this is a multiplication there, I can just distribute that exponent through to both. And let's give you an example of this. So what if I had 2 times 3 to the 4th power? Well, again, I would just distribute that 4 through to both of those, and I would get 2 to the 4th times 3 to the 4th. And hopefully that makes sense. And if we broke this up, and you know, like we've done with the other ones, I would have 4 sets of this 2 times 3, right? Let's maybe take a look at that. I would have 2 times 3, there's 1 set. 2 times 3, there's 2 sets. 2 times 3, there's 3 sets. And then 2 times 3, there's 4 sets. And multiplication being associative, I can rearrange this however I want. And so this would really be the same. I could, pair up all of my twos, right? Pair up my twos, and I've got 1, 2, 3, and 4 there that I can see. So I'd have 2 times 2 times 2 times 2. Multiply that all by my threes, which I can see that I have 4 of those. So 3 times 3 times 3 times 3. And then we could simplify each one of these pieces right here with an exponent, right? So shorten it up and just tell it or communicate how many times to multiply each one of those. And I would have 2 to the 4th, since there's 4 of those, and 3 to the 4th, since there are 4 of those. Okay, hopefully that makes sense, guys. And then our final rule of exponents here, guys, is number 7, is going to be the same principle, just with division instead. And I think that you guys are getting the hang of this, hopefully, from watching this, and understand the idea here that because we're still using division and multiplication between these, that exponent is just going to distribute through, and I'm going to have x to the a divided by y to the a power. Okay, and it would be the same thing here, but this is a really good one to know, by the way, with dealing with fractions, because whenever we take two numbers and divide that, we've got a fraction. And a lot of you guys start to panic when you deal with the exponents of fractions, but realistically they're not too difficult, and I'll give you guys an example here in just a second. So hopefully this makes sense. But let's see what happens when we have a real fraction there. What if I had 2/3, right? 2/3 to the, let's do one that's not too complex, to the 3rd power. Realistically, I could just distribute that through, and I would have 2 cubed over 3 cubed, right? And that shouldn't be too bad, or too difficult to think about. But if it helps, we can multiply this whole thing out, right? I'd have 2 times 3, or sorry, 2 divided by 3 times 2 divided by 3 times 2 divided by 3. And whenever we're multiplying with fractions, remember, we just multiply straight across. So I would have 2 times 2 times 2 on top, right? Let's rewrite this as 2 times 2 times 2 on top. And then on bottom, I would have 3 times 3 times 3 on the bottom. And we can simplify each one of these, or the numerator and the denominator, by writing it with exponents, right? We don't need to write all that multiplication out. That's where an exponent is for. And so I would have how many 2's on top? Well, I've got 3 of them. So it would be 2 to the 3rd power divided by 3 to the 3rd power. Okay, and hopefully that makes sense for you guys. I don't think that this is that complex, and most of this you guys are probably actually familiar with. Okay, one last thing I do want to talk about just really briefly, as it kind of pertains to these exponents that we've been dealing with, and that's fractional exponents. And some of you guys may have seen this already, but let's just talk about this for just a brief second. Whenever we have something like the square root of x, and as we deal with these quadratic functions, you will see this come up, especially as we get into the inverses of these quadratic functions. You're going to be dealing with the square root of x. Well, understand that the square root of x can be written as an exponent instead of a radical here with this, square root sign, by making it a fractional exponent. And that would look exactly like this: x to the 1/2 power. So what happens here, guys, and we could write this in, what happens here is that we get this little, we have a little exponent right here, or not exponent, but root right there, and exponent right here. Okay, and this piece, okay, our root piece here goes into our denominator spot, while our exponent of this thing goes into our numerator's position. And let's look at another example here, just to kind of set this home for you guys. Okay, what if I had something like this: the square root of x to the 3rd power? Well, I can write this as an as a fractional exponent by simply identifying what's going to be in my denominator and what's going to be in my numerator. Whenever I have roots, I'm going to have that fractional exponent. So let's write our x here. I'm going to have a fractional exponent, and then what goes in the numerator and what goes in the denominator. Well, if I go back over here, you'll remember that our root, or the power of our root, will go into our denominator spot. So in this case, this is a square root. If there's nothing written there, it's actually really a 2. So I know I'm going to have a 2 down here, and then my exponent here of my x will go up here into my numerator spot like so. So I would have x to the 3/2, which you could also write as a decimal if you wanted to, which would be x to the 1.5 power. Okay. You're going to see all different types of these as we progress, but let's just cover a couple real quickly. So if I have the third root of x, that's really x to the what? Well, my exponent here is a 1 because there's nothing written, right? So it's going to be a 1. And then my root is to the third power, so that becomes my denominator. And I have x to the 1/3. And hopefully you guys are starting to see a little bit of a pattern here, but what about if I have x to the 4th? Sorry, the 4th root of x. Well, then that's going to be x to the, in the numerator I would have a 1, right? That's my power. And then in the denominator I would have a 4. Okay? And we could continue on all the way down to infinity. This isn't going to change, okay? This same principle applies, and if I have the 5th root of x, well, then I would have x to the 1/5 power, okay? And we could even make one a little bit more complex. What if I had the 5th root of x to the 7th? Well, remember that 7 is going to become my numerator of this fraction, so I would have the x to the 7 over 5. My 5 being the root and the denominator. Okay, hopefully that makes sense to you guys. We will deal more with these, and if you guys ever have any questions, obviously come and chat with me. Okay, thanks, guys.